Chain rule turns out to be relatively simple, provided you understand what it means. In the simplest case, let's say that you have some function g of f of x. Chain rule tells you that if you want to differentiate this composite function, all you have to do is differentiate the inner function and multiply it by the derivative of the outer function. What does this mean in practice? A nice way to also write this is in terms of Leibniz notation. In this case, we can write that dg dx is given by dg df df dx. And what we're doing here is we're writing g as a function of f and then taking f as a function of x. We are, of course, doing a lot of examples so that you get your practice back in case you don't remember how to apply chain rule systematically, and this will be crucial throughout your physics degree. The simple secret to using chain rule correctly is really just to identify the functions you're doing. Sometimes you can have composite functions of 2, 3, 4, sometimes just 2. In this case, once you have identified f of x and then g of f, makes it quite simple, especially if you use Leibniz notation. You can just focus on getting the derivative of dg in terms of f and then f in terms of x. And here I'm purposely doing it in the reversed order to the lecture notes so that you understand that the letters don't really mean anything. And if you understand how to use chain rule, you can use f and g interchangeably. And in this case, you can also recognize that this is g of f of x. And in this case, this component is just f of x. So I've actually written it the other way around because we're multiplying it also. It doesn't matter the order you use it. But thinking about these infinitesimals, these quantities, remember, they're not quotients of real quantities, but sometimes it helps thinking as if they are. Leibniz notation is really helpful because you can realize that you could kind of cut the df's and you recover dg dx back. This is why Leibniz notation is so useful and intuitive, but you're not really looking at quantities that you're cutting out. You should always use cutting out, but it's just cutting out, okay? There's nothing like trying a first example to make sure we understand how to use chain rule. Let's say we want to differentiate the function that's in your lecture notes. That's section 5.6.5. In this case, the first step is to recognize whether you're dealing with a composite function. In this case, you clearly are, which means you should start identifying the functions. In this case, if we follow the lecture notes, we can identify this as function I. We can identify this as h. So you could write this as h of I, which is then a function of x. And the entire thing as y. If we use Leibniz notation, we can write that the derivative of y, this is dy dx, is given by the product of a few derivatives. First of all, we want dy of dh. We multiply by the next one because h is also a function of I, dh di, and finally I is a function of x, so we multiply by di dx. Leibniz notation is really powerful because of this. You could keep going into the functions until you reach the final one, and it also means that you can calculate these independently and then simply multiply them. For example, we want to calculate dy dh. All we have to do is use the power rule. We drop the exponent it becomes 2, 1 plus cos of 2x. If we want to calculate dh di, all we have to do is look at this expression. In this case, this does not depend on I. This does, and the derivative of cos I is minus sine I. So it means we get minus sine of 2x. And finally, di dx is the derivative of 2x, which is 2. And we can then plug in, we can say this is term 1, term 2, term 3. We plug them in here, and we get 2, 1 plus cos of 2x multiplied by minus sine of 2x multiplied by 2. And you can simplify it just as you can see here magically appearing and also in the lecture notes. The big secret though is to identify within Leibniz notation that when you're calculating the derivative of y in respect of h, then h becomes the variable and you ignore anything else. And then you move along. When you're calculating a derivative of h in respect to I, then this is a variable. Sometimes it is helpful to explicitly have it like this, and then you sub it back later on, or you can do it straight away, just like I did it. The trick though, just like for limits, the ultimate secret to using chain rule perfectly is practice a lot. There's just nothing like it. I would encourage you to have a look at the other example in the lecture notes, and in the discussion sessions we may do others. And if you have questions, just let me know via Teams or email me. Let's get the board ready for logarithmic differentiation, implicit differentiation, and parametric differentiation with a little bit of good old physics one-on-one magic. Definitely still working. See you in the next video.